Now online, now live. 100% link out.
Okay, separate scientists. Okay, we're back live again. We had a little bit of an interruption there because so let's just remember what the rules are around reflection. So I'm just going to draw here a plane mirror, and you can see that I'm using a ruler. It is super duper important. Okay, and I'm going to draw a diagram to represent how light behaves when it shines onto a plane mirror. Now, the first thing I'm going to do if I'm doing any of these diagrams is I'm going to place in my normal. Now, on your exam tomorrow, they could give you a ray of light that's hitting a mirror and say, complete it. Now, I need it to hit my mirror where it hits the normal. So you could actually have this as your starting line, okay, drawn by the exam board, and they say, finish it off. So the first thing I've done is I've actually added the arrow to say that's my incident ray. Okay, and the angle at which it's hitting the plane mirror is always calculated between the ray of light and the normal. So that's my incident. I'm going to put a degree sign there for angle. Now, I've got to complete this diagram by showing the reflected ray. Now, I know that the angle of incidence equals the angle of reflection. Now, in your exam tomorrow, if you've got to do one of these, they would be looking for you to actually roughly get the correct angle. Now, I'm trying to be really precise here, okay? And I'm being precise using my pencil and my ruler, and you should use a pencil and a ruler, not a pen, okay? I want to make sure that all my lines are touching each other. If the lines aren't touching each other, okay, that means that there's a break and the light is not continuing forward. And that's my reflected ray, okay? So when I look at that, I can see that this angle and this angle are roughly the same. So that's following the rule of the angle of incidence equals the angle of reflection. Okay, so angle of incidence equals angle of reflection. Okay, so that's the first do refraction, whereas you need to do reflection. So here I've got an example of a diagram, and I'm going to draw it out in a much neater way. Okay. So there is my reflective surface. Okay. Now, I would normally use a pencil for this, but I've only got pens here this evening. I still need to have the idea of my normal. So I'd put a very faint pencil line in so that I know how my normal behaves. Okay. So in this case, all right, as we're seeing here, we actually have some wavefronts, okay, going towards the mirror, and then we need to roughly have them moving away, okay? So if I put a line in like that, and you do it, it'd be much neater. Those angles are roughly the same. So a wavefront is just actually showing, okay, the top of a crest of a wave, okay? So that's how we do our wavefront diagrams. Now, before I go on to look at lenses, I'm just going to remind us about white light and how it breaks up into its spectrum. So remember when we did about the electromagnetic spectrum, we had Ryan, my improper vicar, uses X-rated gags, okay? Now, visible light or white light can be broken up into the spectrum, okay? And the spectrum is red, orange, yellow, green, blue, indigo, violet, okay? Now, I'll stop saying okay. So when we actually think about those colours, well, I stands for infrared and U stands for ultraviolet. And this is important for your space physics, really. Just remember, it would go red, orange, yellow, green, blue, indigo, violet, that order. longest wavelength, shortest wavelength, lowest frequency, highest frequency. Okay. Now, we do need to know what colour white light is made up of, because that allows us to see different objects. So if I've got a lovely juicy apple here, okay, and it's a lovely juicy red apple, okay, I can see it's red because every single colour from the spectrum is hitting it, but only red is being reflected. So all the other colours, orange, yellow, green, blue, indigo, violet, are all being absorbed, but red is reflected. Okay, that's how we see colour. The other thing I want you to be able to do is to say, well, what happens if I look at a coloured object through a different coloured filter? So I'm going to take here, okay, my red pen, and I'm going to draw a red hat. Okay, and we know it's a red hat because red light is reflected off it. But I'm going to look at that red hat through a blue filter. Okay, so there's my blue filter. All right, I'm going to draw my eye here. So I'm looking at my red hat through my blue filter. Well, what colour would my red hat really look like? Well, if I popped around the side, it would look red. But when I'm actually looking at through the blue filter, my red hat, in fact, looks like a black hat. And it looks like a black hat because the red light is absorbed by the blue filter, because it will only let blue light go through it. So if I had a yellow hat and I had a red filter, my yellow hat would look black when I look through the filter. Okay. If I had a red hat and it was a red filter, it would look red because it would let the red light through. Okay. So that's just the key things around how we actually see colour, and we look at reflection and we look at refraction. Okay. Now, I'm going to go on and I'm going to look at lenses. Now, remember, when we're looking at lenses, we've got two types of lens. We've got a convex and a concave lens. All right. So we need to remember what the shapes of them are. So a convex lens is like an oval shape, and on a diagram, it would be represented like that. Think about the arrows as being these parts here, okay, and the line represents the exact center. Whereas a concave lens looks like this. It's a little bit like, think about it, concave, that's the entrance to your cave. And so that would be represented by a line that looks like this, okay? Think about that Y there, that's the center. Now, it's very important that we understand that when we're doing drawings to do with lenses, we're always talking about the focal length from the center of the lens. So we're talking about here and here. So this is why we use these line drawings rather than lens, because we want it to be in the center and in the center. And that makes it much easier for us to work out. So if I was actually doing a drawing of a lens and how a light behaved, I would use a graph axis. So my vertical is representing my lens, and I would have an horizontal, okay, and right in the center here is representing the center of both of those lenses. Now, there are a number of diagrams, or should we say, there are a number of ray diagrams that you've got to draw for lenses, and any of these could appear tomorrow. We've got 6 of them that I'm going to show you how to draw, okay, and then work out what kind of an image they are. Now, just remember that a real image is something that would be formed on a screen, whereas a virtual image is something that looks as though it's coming from a different point. For example, like the image in a mirror, it looks like it's coming from behind the mirror. So the first diagram that we're going to do is diagram 1. I've put a little 1 on here so that you can play it back and you understand it. And it's an object that's beyond 2F, okay? So that's our focal point. That's using our pencil and our ruler. And please, 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 tomorrow, use a pencil, not like I'm doing a pen. And so it hits our vertical axis. Now, that's the center of the lens. And then it goes down through. And the accuracy at which you draw this is absolutely important. So draw with a sharp pencil, sharpen it. So that's our first line. Our second line goes straight through the center of our axis. And you can see that I'm slightly off. Okay. And our third line goes from the tip of our object through the focal point on this side, down to the axis, and then across. Now, where all 3 lines join together, okay, that's where our image is formed. Now, because we could project that image onto a screen, we would say that that's a real image, okay? It's upside down compared to our object, so we'd say it's inverted. And we can see that it's smaller, so it's diminished. Now, I can't stress to you enough of how important it is that you use a sharp pencil, you take your time, and you make it accurate. Because you can see here on my diagram, I've not gone through the center because I'm using pen. I'm slightly out here. And that could affect where my image is, and it could change its size, which could then lead you to say something that's not quite right about it. So that's when our object is beyond 2F. So what happens now if our object is at 2F? So it's the same principle. I'm going to do it a little bit quicker, and I'm not going to really talk through it. So I have my line that goes to the axis. It goes down through the focal point, okay? I then have it going straight through the center, trying to be as accurate as I can, but with speed, through the focal point, and then across. So our image is now formed here, and I take it up, okay? So our image is real, inverted, and it's the same size. Okay? All right, so that's our second one. Okay, oh, these sharps are getting a little bit strong. I'm going to change colours now. Okay, my third one, okay, is when my object is between 2F and F. So same again, practice makes perfect. I'm sure you've all heard that before. So I go across, okay, I go down, I go across the center, okay, and then I go down. Okay, might not have made my lines long enough. Always the case. Always make your lines much longer, because again, if you have to add to them, okay, it can lead to a bit of error. I've not got those exactly right. That's not going through the center there. That's not quite. But my image now magnified. If we go to diagram 4, which is when our object is at F, so same principle, to the top, through F, then from the top, through the center, OEC, it's on F, so I can't go through there. Okay, I'm looking at that, I'm going, oh, the lines aren't crossing over each other. I'm going to have a little look now. If I put my ruler on that way, I put my ruler on that way. They're not going to cross over behind there. So I'm going to get no image. Okay? Now we're practicing doing these just so that we can actually draw them in A and then to there and through. Now straight away, some students would go, oh, there's no image there. But okay, I put a little eye there to actually think about this. I'm going to just swap colour, okay? And what I'm going to do is I'm going to track those rays backwards, like that. And I'm going to track that one backward. Okay, now we can actually see that our image is being formed here, okay? And this time we can say that it's virtual because it's actually coming from somewhere that it really isn't, okay? It's upright and it's magnified. And you can see it's on the same side as the object. And then we have our last one, okay, which is, note that all of those were convex. It's a concave lens, okay? So we have to think about how we actually draw this. So remember, with a concave lens, it's a completely different shape, okay? So I'm just going to do that for a second. I'm just going to remind you, it's this shape. And this causes, when light hits the center, it goes straight through. When it hits here, it diffracts up. When it hits here, it diffracts down. So we need to know how to actually draw that, okay? And what actually happens with this one is to understand how it diffracts. We go, whoops, sorry, there, just like that. And that should be a dotted line, okay? All right. And then we actually go with this one. We go through the middle again. So, okay, like that. All right. And, oh, I've completely messed that up. I'll come back to that one, boys and girls. Okay, I need to get another little drawing. I've just messed that one up. Okay, all right. If I don't get another drawing, I'll actually put that up onto it later. I'll print it. I'll put it up onto the outside of school later on the doors. But you do get a virtual image. It's upright and it's closer to the lens. In fact, it's there. There we are. That's where it crosses over. All right, yeah, I had done it right. I thought I'd done it wrong for a second. So our image forms there. It's virtual because it's on this side, okay? It's upright and it's closer to the lens than the original object. Okay, so I just thought I'd done that one wrong for a second. And with it being in pen, you can't easily rub it out, okay? So the next thing that we're going to finish off with for waves is all about sound, okay? Now, we did a little bit about sound and longitudinal waves earlier on, but let's concentrate on ultrasound. Now, human hearing is 20 to 20,000 hertz. Ultrasound is above 20,000 hertz, okay? Now, what we need to really understand about ultrasound is some of its uses, okay? So, when we actually use ultrasound, I'm going to use this as an example, okay? Here's our ultrasound emitter, all right? And it's also a receiver. Now, when we emit ultrasound, our wavefront goes out and it hits this boundary, and I'm going to use a different colour, it bounces back, okay? Some of it will continue, and when it hits that boundary, and I'll use a different colour, that bounces back. So we actually say ultrasound is partially reflected. Now we can use this property to work out the distances between boundaries of materials. So that's sort of like how we work out what a baby looks like in the womb of a woman when she's pregnant. We can also use it if, for example, I've got a material here and I'm scanning it to see what the quality of it is. If there are cracks in it, the ultrasound reflects back earlier than what we expect, and we can actually then see, okay, what actually, that it's something wrong with it. And remember, when we're actually working out maybe the distance, we're using distance equals speed, okay, multiplied by the time. So if we know the speed at which the ultrasound is traveling, we know the time it takes to reach the boundary and come back. Remember, it's there and back. We can work out its distance. Now, we sort of like use the principle of sound to look at the structure of the Earth, okay? And one of the things that you need to be able to do tomorrow is be able to actually say potentially, what is the structure of the Earth and how do we know? So I'm just quickly doing a drawing of the Earth, okay? So we have on the outside the crust, we have the mantle, we have the outer core, and we have the inner core. Now the crust we know is solid, okay? We actually know that the mantle is so like a liquid, the outer core is liquid, and the inner core is solid. All right. Now we understand the structure of the Earth through looking at the waves created by earthquakes. Okay. And earthquakes are made out of two types of waves. We have primary waves, or P waves. Now, P waves are longitudinal. They travel faster than S waves, and they will pass through solids and liquids. So, if we had, for example, an earthquake here, okay, the wave will pass through the solid crust, through the semi-solid liquidy mantle, through the outer core and the inner core, and we could maybe detect them here, okay? So they will travel all the way through. We'll detect them in lots of places, okay? Whereas with our S waves or secondary waves, they are transverse, okay? They are slower and they will only pass through solids, okay? So what we actually find, if our earthquake is here, they don't travel as far, okay? And we use that information to work out the structure of the actual Earth. And that's how we determine, because nobody's ever been to the centre of the Earth. If they did, they'd be a little burnt crispy crisp, okay? That's how we work out roughly what the structure of the Earth is. So remember that P waves are longitudinal, pass through solids and liquids. They're faster than S waves, whereas S waves are transverse, and they will only pass through solids, okay? They're much, much slower. Now, I'm just going to finish off with the waves, because I'm really conscious of time, okay, by just talking about what a true black body, a perfect black body object is. Now, a perfect black body object is something that absorbs all of the radiation, okay, that hits it. All right, it absorbs it all. None of it is reflected and none of it is transmitted. It absorbs absolutely everything. Okay, so that essentially brings to the end, okay, the separate sciences part for waves. Now, what I'm actually going to do now is just go through a few bits of electromagnetism, okay, that you need to know. I'm going to do that fairly quickly, okay? So we've basically done the motor effect. We've done Fleming's left-hand rule, okay? What we need to really go through is the generator effect, loudspeakers, okay, and transformers. So if we go back to our permanent magnets here, like we had before, with our north and our south, and we have our coil that's in there, okay? If we actually have our coil attached to something that's going to rotate, like, for example, a turbine, and our turbine is spinning it round, as our turbine spins our coil round, okay, the wires are going to keep cutting across the magnetic field, okay? And as the wires spin round, so if I do a little side-on view here, there's our magnet, north and south, okay? There's our coil. 1 minute it's like this, north and south. Next minute it's up. So all generators produce alternating current. So think about it like this. Generator A for alternating current. And if it's alternating current, it's alternating potential difference. Okay, so sometimes it does actually ask about the potential difference because you can't have current without potential difference. Now, if it asks you to draw that or to recognize, is it a generator that's making this? Okay, on an oscilloscope, alternating current goes like this, positive to negative. Okay, like north, south, north, south. Now, if we're talking about a dynamo, okay, a dynamo is similar to a generator. However, a dynamo makes direct current. Dynamo, direct. And on an oscilloscope, that would look like this. You can see we've got the positive, no negative. Okay, all right. So that's our generator effect. And they might ask you there about what does a dynamo and a generator actually look like. Generators, alternating current, alternating potential difference. Dynamo, direct current, direct potential difference. Okay. I'm now just going to quickly go through how a loudspeaker works. And a microphone works in exactly the same way, but in reverse. Now, for your loudspeaker, you need to have a permanent magnet. And our permanent magnet looks like this. It looks like a big E. But we have here a north. Here is north. So if we actually looked at it on the side, if we could see it, it would look like that and like that. That outer bit there is north. That middle bit is south. This bit here is a south. Okay. Now, going around that, we have a solenoid. And I'm going to draw it like this. Okay. And that solenoid is attached to a paper cone. All right. Now, our solenoid, all right, it has to be a complete circuit. So I'm going to take some wires off here. Okay. Now, when we're playing our music, all right, we get electrical signals, current, going through our solenoid. As it goes through our solenoid, it makes a magnetic field. That magnetic field interacts with the ends of our permanent magnet, and it causes our cone to move backwards and forwards. And as it's moving backwards and forwards, it's creating, you get it, sound waves. So we have the creation of our compressions and our rarefactions. That's how we hear. So as it's going backwards and forwards, it's pushing particles together, separating them out, creating sound. Now, The same principle is for our microwave, but instead of having a cone, our microphone has a membrane, and the sound waves hit it, which make it vibrate. They're definitely not robots in disguise. Okay, so there's no Optimus Prime and there's no Bumblebee. Okay, it's just a boring old, metal core. Okay, when I was a kid, it was Transformers, robots in disguise, fighting against the evil of the Decepticons. Okay, so there's our metal core. Now, very important, it's our iron core. Now, if I do it at top view, our iron core would look like this. And if you've ever taken a transformer out, it's actually made of layers of iron with something between it. It's called laminated. And it's laminated because that makes sure that our magnetic fields are better, and therefore our current is better. It's not going to fluctuate. Okay. Now, a transformer is our iron core and then with two coils that go around it. So I'm going to have a coil that comes here. Okay. And that's what we call our primary coil. And then we've got a secondary coil. Okay. All right. Now, when I actually look at this transformer, I can actually see that my primary coil has got 1, 2, 3, 4, 5. It's got 5 lots of wire on it, whereas my secondary coil has got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's got 10 coils. Okay, so that would tell me that this is a step up transformer. Okay, so this means that when I pass current through here, okay, it's going to induce a magnetic field around it. So remember what we did earlier with our solenoid, because all it is a solenoid. Okay, we're going to get our magnetic field that comes out. Okay, as the current is flowing through it, it's creating that magnetic field. That magnetic field is going to cross the second coil, which is going to induce a current. And this means that our current, because there's more coils of wire, is going to go up. Okay, so a step-up transformer increases the current. Okay, the current goes up. All right, so the opposite would be a step-down transformer, which would mean that the current would go down. Okay, all right, sorry, the potential difference goes up, the current goes down. Okay, so that's the last little thing I'm going to do there about transformers. Just a reminder that space physics, I actually did that in intervention yesterday for students who came up, and that YouTube video is already uploaded. Okay, so thank you, ladies and gentlemen. It's been an absolute pleasure. Both myself and Mr. Schuller have had a really busy day, but we've enjoyed doing this for you. Make sure you revise, and we'll see you tomorrow morning in the exam.
Good luck, you, and bye.